Hello and welcome to another live show here on Slooh.com. My name is Will Gater, and tonight we're celebrating that most beautiful of all the planets, the ringed world Saturn. Now, over the course of this show, we hope to bring you some live pictures from our telescopes in the Canary Islands. We're fighting a few little technical issues at the moment, but we hope to bring you those pictures later in the show. But as well as that, we're going to be delving into some of the real mysteries of Saturn. Later on in the show, I'm going to be speaking to planetary scientist Professor Jonathan Lunine from Cornell University about some of the moons that orbit Saturn. Maybe could there be places where primitive life may be able to exist orbiting the planet? We'll find out more about that later on. Of course, here on Slooh, we love hearing from you, and we love hearing about your observing stories. So if you're out observing Saturn tonight, or maybe you just have very fond memories of looking at the telescope and looking at Saturn through the telescope, then you can always send us a tweet through social media and Twitter using the hashtag #SuperSaturn. And that's also a great way of asking us any questions during the show, and we'll put those to our experts live on the show. But before we go on to that, I want to introduce a great friend of Slooh astronomer Bob Berman, who is the author of Zoom, How Everything Moves. Bob, it's great to have you on the show.
Pleasure, Will. Great to be back here.
Saturn really is one of those planets that I think has captured everyone's imagination who's ever looked through a telescope at it. What are your memories of observing Saturn over the years?
Well, it never fails to amaze us. You know, it makes people jump up and down and clap their hands and say, "That's not real," and "Oh my God." And nobody who looks at Saturn fails to be amazed. And look at the image that we're seeing now. Now, of course, this is not a live view. This is a spacecraft view. But if this isn't something out of modern art, what is? You're seeing one of its satellites, and it looks like it's skewed by a straight line. No, those are its rings seen perfectly edge on. And because the rings go around its equator and the moons go around its equator, well, when you're in the right lineup, you get something like this. And look at the shadow cast by the rings on that curved body of the planet. I mean, I'd hang that in a museum, wouldn't you?
Oh, absolutely. Yeah, we're going to be talking a lot, I'm sure, about the Cassini mission and these extraordinary pictures that it's returned. I just thought, why is tonight special, Bob? Because in the build up to this show, we've been talking about Saturn as being at opposition tonight. What does that mean?
Well, it means the sun and the Earth and Saturn are forming a straight line in space, so that if you look in the opposite direction from the sun, you'll see Saturn. Or, put another way, as the sun sets, Saturn rises. When the sun is at its lowest point, Saturn is in the opposite part of the sky at its highest point. And just as the sun rises, that's when Saturn sets. So it's opposite the sun. That's a straight line, and that's the occasion when Saturn is closest. Today's the day.
And tonight's the night, and presumably that means it's a great time to observe it.
Yes, it's at its largest of the year, and more than that, its rings, although they look edgewise in this Cassini image, are actually tilted now very favorably toward us. So we see the rings beautifully, and if our little technical problem gets straightened out, we're going to have just gorgeous views of the rings because that's pretty much close to optimum right now. So this is really the night. Saturn also does something a little different from other planets. The same night that is closest to Earth is when it's at opposition. That's not true of every planet. For example, next year, Mars will come to its closest point a whole week, in fact, more than a week, after it's at opposition. So the two don't have to exactly coincide, but it does with Saturn tonight.
So really, tonight is the night for Saturn. Then, I think one of the most interesting things about Saturn that you touched upon it are those rings, and we had a great Twitter question early on from someone using the hashtag Super Saturn, and they asked us about what effect the sort of brightness of the rings has on the overall brightness of the planet. What's going on there?
Well, the ring double the brightness. When they're tilted at any kind of angle other than edgewise, Saturn gets brighter and brighter and brighter in the sky. Right now, it's uh, about magnitude zero. So those who know a little bit about astronomy know that that pretty much matches the star Arcturus, the brightest star of the spring sky. And if you look down in the southeast, if you're in a place where Saturn is just rising, you'll see it as the brightest object in that part of the sky. So the rings are largely responsible for it. They more than double the brightness of Saturn. That's because they're made of chunks of plain water ice. And as we all know, ice is shiny, it's reflective.
And if someone wanted to go out this evening and maybe they're watching the show and they wanted to go out and actually see Saturn, where would they have to look?
Well, it depends on the part of the night, but if during the first few hours of the night you'd look into the southeast, and we're showing you an all sky view now taken at the Canary Islands, but this shows what you'd see. Right there in the center bottom of the picture is the head of Scorpius, the almost vertical line of three stars perfectly. And those three stars, Beta, Delta, and Pi Scorpii. And look at that bright object just to the upper right of the uppermost of those three stars in a row, and that is Saturn. Another little key is the reddish star Antares, one of the reddest stars of the sky, of the bright stars in the sky. That's the heart of the scorpion. So that comes up, and as the night goes on, it gets higher and higher. For you people in Britain, I'm afraid the tail never clears the horizon. For we in the middle or northern part of the United States, the tail kind of scrapes along the horizon like a vacuum cleaner. It never gets up very high. But if you live in Florida or places even south of there, that's when the constellation is at its most beautiful. The tail is higher in the sky, and that's why a lot of people have a hard time deciding which is the finest constellation of the 88 constellations. Is it Scorpius or is it Orion? And oddly enough, in mythology, you can never compare them because in mythology, the scorpion killed the hunter, Orion, and so the gods wisely separated them maximally by making sure that they're never up at the same time. When Orion is setting, that's just when Scorpius is rising.
So we know where Saturn is in the night sky. There's that lovely picture from live from the Canary Islands. That's our all sky view with a beautiful Milky Way there. But let's put things in context and let's talk a little bit more detail about some of those mysteries of Saturn. I want to bring in now our guest, Professor Jonathan Lunine from Cornell University. He's a planetary scientist and someone who has studied Titan and the moons of Saturn, and even Saturn itself in quite some detail. Professor Lunine, thank you for joining us this evening. It's a fascinating world, Saturn, isn't it? I think he might not be. We might not have Professor Lunine on the line right now. But Bob, let's look at this picture we've got from Cassini, because Cassini is the mission that I think has really shown us Saturn in incredible detail. What do you have a favorite image? I mean, we've been looking at literally hundreds of pictures today of Saturn
Well,
trying to
this is
pick the
great.
best
This is
ones.
great, Will, of course. But what you can never ignore is that thing on the North Pole of Saturn, because this happens to be the time when the North Pole is tilting almost as far toward the sun and toward the Earth as it can get. Next year, it'll be a little bit more, but it's perfectly well seen. And look at the North Pole. There is the famous hexagon. Now, how do you get a hexagon where each one of the sides is the diameter of Earth? So this is a large hexagon, almost a perfect looking hexagon. Now, considering that the winds that are blowing there are blowing at tornado strength, hundreds of miles an hour, more powerful than a hurricane. So how do you have a structure that maintains its integrity without those kind of winds? And if we get the professor on, that's one of the first things we want to ask him is
Yeah.
what's going on?
I think that there are so many questions, aren't there, about the Saturn system that I think you and I have, Bob. Hopefully, Professor Lunine will be able to sort of shed some light on them. I believe he's now on the line. Professor
Good
Lunine, thank you
evening.
for joining us. So when did your interest in Saturn and the Saturnian system begin?
Well, I was always interested in Saturn as a kid. I was interested in astronomy. Saturn's a great object. It's fascinating for everyone. But as a graduate student at Caltech, I became interested when Voyager 1 flew by Saturn in 1980, and particularly the flyby of Titan, the close pass of Titan, kind of sealed my fate for the rest of my career.
Was that the time that we really got the sort of first glimpse of Titan as this sort of very unusual moon? It has a very thick atmosphere, doesn't it?
It does. Of course, the Dutch-American astronomer Gerard Kuiper was actually the one to discover the atmosphere by measuring methane lines in the spectrum of Titan, but it was Voyager 1 that told us that the atmosphere was actually mostly molecular nitrogen, very dense, 4 times denser than the air at sea level at the surface of Titan, and very cold. But not as cold as it might otherwise have been. There's a greenhouse effect that elevates the surface temperature by about 10 degrees Celsius from what it would otherwise be. So it really was Voyager 1 that gave us the basic parameters and set the course for the US and Europe to pursue what would become the Cassini-Huygens mission.
And that thick atmosphere, it's not the only sort of unusual thing about Titan. It appears to have from the Cassini images. We've seen sort of rivers and lakes.
Yeah. So of course at the time of Voyager 1, we could not see to the surface. Voyager 1 had Vidicon tubes. Their wavelength reach was limited. It was Hubble that gave us the first near-infrared views of the surface, but it was Cassini that discovered the river channels on Titan, the lakes and the seas, and mostly the northern hemisphere, but a couple in the southern hemisphere. And in fact, Cassini is so good that it has been able to do things that we just did not think about when planning this mission. The radar on Cassini has been used as a kind of a sounder that has penetrated to the bottom of the large seas, told us the depth of these seas, about 160 or 200 meters, and then by measuring the attenuation of the radio signal we've been able to determine the composition of those seas and, in fact, confirm that they're liquid methane and ethane.
So we can actually see in these incredible, and I believe these are radar pictures, these sinuous structures. Presumably, they've been carved by those liquid hydrocarbons on the surface.
Yeah, that's almost certainly the case. And you see them feeding into one of these large seas on the right-hand side. So these are really flooded canyons, and the topography in and around these large seas is pretty rough. In fact, even before the radar measured the depth directly, just by looking at the topography, it was estimated that the seas might be 100, 200, 300 meters in depth. It's like the canyons in the American Southwest in many ways. It's really remarkable, but it's not liquid water, it's liquid methane.
I think that's what people will probably watching the show will probably find absolutely remarkable. You know, the sort of structures we're seeing are so familiar, and yet they're formed by this, well, I guess, quite alien sort of interaction. It's a little bit like Earth's water cycle. Would that be fair to say?
Everything that Cassini has told us, and I should add to that, the Huygens probe, which was the European Space Agency, the flying saucer, if you will, that descended to the surface, released by Cassini, and actually landed on the surface and measured, after photographing channels, small channels on a hillside. Once the Huygens probe landed, methane and ethane and other organics came pouring out of the surface, evaporating into the mass spectrometer on Huygens. So what the two have together shown us is that all of the elements of the Earth's hydrologic cycle, except for a globe-girdling ocean, are present on Titan. What Titan lacks is anything larger than the Caspian Sea, essentially. And so most of the surface is dry, but in the high northern latitudes we have these areas of extensive seas, the largest of which is like the Caspian Sea. So other than that, Cassini has shown us methane rain, methane clouds, methane rivers, streams, methane lakes, and methane seas. And the seas are a composite of methane and its daughter molecule, ethane.
From everything we've learned from Cassini and Voyager before it, what do we know about how Titan got like this? I mean, where did it get this atmosphere from, and how did it sort of become so big?
Well, those are two of the $4 billion questions, I guess. The first one is, why is Titan so big as a moon itself? And it's interesting to note that there are three ice rock bodies in the outer solar system that are virtually identical in size. Ganymede and Callisto around Jupiter, and Titan around Saturn. And a clue to why they may have reached the size they did and not larger is that the energy released during their formation was about the energy that is released on a per gram basis by vaporizing water by the time they got to about their present size. So that might have set the limit. Now, why is Titan so different from Ganymede and Callisto in the sense that while it's the same size and density, a body of ice and rock like Ganymede and Callisto, it's got this enormous atmosphere of nitrogen and methane, which Ganymede and Callisto lack completely. And if we can understand that, we will probably understand a lot about the conditions in the early solar system. But one possibility is that Saturn, of course, formed farther from the Sun than Jupiter did, and Saturn is much less massive than Jupiter by a factor of about more than a factor of 3. So the environment around Saturn was always colder than the environment around Jupiter. There was less radiation from Saturn itself to the disk of material from which the satellites form, and the Sun was farther away. That might have been just enough to allow methane and probably ammonia as the parent molecule of nitrogen to be trapped in the building blocks from which Titan formed. And then as that heat of formation, that heat of accretion began to rise, those materials were liberated from these building blocks and formed an atmosphere. Ganymede and Callisto, on the other hand, around Jupiter, too hot, couldn't get those materials trapped in the water ice, so they never had a chance to make an atmosphere.
So, I mean, when we think about or when we look at Titan, we see a world that has a thick atmosphere. It has lakes and sort of very Earth-like features. I guess naturally we might sort of start thinking about life and maybe, is this a place perhaps where life may have arisen or perhaps the conditions for life? What are your thoughts about that? I know you've done a lot of research in this area.
Right. Well, I'm going to jump the gun on you a bit and say that from my point of view, there are really two targets in the Saturn system that we must go back to search for life. Titan is one and Enceladus is the other. Titan is the place where there are these open bodies of liquid, sources of energy, namely sunlight, not very much, 100 times less than what we get here at the Earth, but still actually enough to energize biological processes, but it's liquid methane. So what kind of biochemistry could work in liquid methane? It's not going to be the biochemistry that we're composed of. It's going to be something else. But there could be other possibilities. There could be other solutions. And going to one of the seas of Titan, landing a probe on that sea, and sampling directly the liquid gives us a chance to find molecules that would be evidence of what's often called self-organizing chemistry, where structures and catalysts are formed and reformed over time, and a kind of an organized chemistry that is in fact at the core of life on Earth, but again chemically different so that it's adapted to methane. That might well be going on in the seas of Titan. If we find that, it tells us that life as a general chemical system, self-organizing, evolving chemical system, doesn't require liquid water and is perhaps ubiquitous on many different kinds of bodies in the cosmos.
Are the conditions that we've sort of found on Titan, are we able to in any way sort of simulate them on Earth to try and understand whether the process you're talking about can actually occur?
There's, well, the organized chemistry is going to be difficult because we can't even do that in aqueous water-based materials or experiments on the Earth. And the reason is the following, that you can make the simple building blocks. So let's go to the chemistry of Earth life as we understand it. And the building blocks are amino acids, nucleic acid bases, and other small molecules like adenosine triphosphate, the energy-carrying molecules. These are all easily made in the laboratory. And in fact, Miller and Urey made amino acids from a spark discharge back in the 1940s. But it's putting those together into the right kind of polymers and generating the correct catalysts and information-carrying molecules that will sustain this process forward. That evidently requires some amount of time and possibly may require a minimum amount of space. That is a large enough area and enough variation in having liquid versus solid, freezing versus thawing, evaporation versus condensation, something like that. There's some evidence, particularly from theoretical studies, that that's the case. Now that doesn't mean it took hundreds of millions of years. It could have taken 100 years or 1,000 years to get these interesting molecules. But as we all know, um, research programs don't last 100 years. So doing this in the laboratory on the Earth is very, very difficult. And that's why going to these natural environments in the solar system, which have been the way they are for a very long time, is really the way to test for life. And with respect to the other moon that I mentioned, Enceladus, very
Mm.
small but geologically very active, and that may well be a place where life as we know it, terrestrial type life, exists today under the surface.
Yeah, and in Enceladus, I mean, we've got these lovely live views from the Canary Islands, but we've also got fantastic Cassini images of those incredible jets, and presumably there, underneath that surface, there's liquid water there that must be powering those, right?
Right. So I would say that Cassini's greatest, it's like saying what is the greatest movie ever filmed, right? But if I had to say it, Cassini's greatest discovery was the discovery of the plume and the underlying jets that feed the plume coming out of the south polar region of Enceladus. Many, many dozens, perhaps 100 jets coming out of the fractures that you see in that image that are outlined in blue. Cassini has flown through the plume generated by those jets, and it's measured the plume materials directly and found not only water vapor and water ice, but organic molecules like methane, nitrogen-bearing molecules. In the ice grains are salts of sodium and potassium that have been directly detected by one of the Cassini instruments that breaks these ice particles up. And then Cassini has also made measurements of the mass distribution of Enceladus that tell us that the ultimate source region of these jets that you're seeing in that image is an ocean about 40 kilometers under the surface, centered at the South Pole, but possibly extending in a somewhat thinner fashion around the entire globe, again about 40 kilometers below the surface. Now, the remarkable thing about Enceladus is that we don't have to drill to test for life or to see whether, in fact, life exists in what is evidently a habitable environment, a saltwater ocean with organic molecules and a heat source. But we don't have to drill, we don't have to land. The plume is, in fact, ocean material. The fact that there are grains containing salts and also other grains containing nearly pure silica tell us that that material is coming from the ocean itself and in part from the interface between the ocean and the seafloor, the underlying rock. So we just have to go back to Enceladus with more modern instruments that have the power and the resolution and the sensitivity to look for biomolecules. We know now from Cassini that Enceladus satisfies the basic requirements of habitability. It will require a new generation of instruments that we have today, send them to Enceladus, fly through the plume, and test for biological activity.
That would be an incredible discovery. Well, I really hope such a mission gets off the ground, if you excuse the pun. And hopefully, in a few years, Professor, you'll be able to come back to us here on Slooh and tell us what that particular mission is found. But thank you so much, Professor Jonathan Lunine, there talking about some of those incredible moons that go around Saturn. We can actually go back live to the live imagery that we've now got from the Canary Islands. We've finally got those live images coming back. And I wanted to bring back Bob Berman, Slooh astronomer. Bob, these are great pictures and they really show that sort of classic telescope view of Saturn, don't they?
Gorgeous, right? I mean, what can you say? This is, it's stunning. You can see, I mean, at a glance, we see that the outermost ring, the A ring, is darker than the rest of the ring. That's obvious. We can see the separation, the black thin gap. It's less than 1 arc second, by the way, in size, which means it's really hard to see, but we can see it clearly through the Great Slooh telescope tonight that separates that outermost thin but darker A ring from the widest ring, the main ring, the B ring. That's the white ring. And now look where it passes in front of Saturn, right in the middle of the image. You can see that there's even a semi-transparent ring. That's the C ring or crepe ring. And it's not opaque enough to completely block out Saturn. You can still see Saturn through it a little bit, the body of Saturn, but you can nonetheless see that there is that third ring there. So we're seeing all the detail. You know, when you're looking through a great telescope, that's what you're looking for. The outermost
Mm.
ring, the Cassini division, the C ring, the white belt that encircles its equator, and the dark polar region. And we got it all tonight.
And that's the beauty, really, of having our Slooh telescopes on top of this island in the Canary Islands, where we've got a beautiful view of the night sky, sort of unhindered by sort of pollution and muck that we get usually. And so let's go back to basics, actually, because we were talking about the rings, but what are they made of, Bob?
They're made of chunks of ice and changing in size from beach balls to even small bungalows to perhaps even baseballs. It was a moon that came too close to Saturn. The rings are just within what's called the Roche limit, ROCHE, and when any object ventures that close, This is 1.5 times the Saturn radius. It cannot withstand the tidal forces, so it breaks into 2, 4, 16 innumerable pieces. So that's all that's left of what once was a moon. But notice how it passes right behind Saturn. This is our test, Will, of the angle of tilt of the planet. See, the planet has almost a 28-degree tilt to its axis. So sometimes during its 29.5-year orbit around the sun, we're seeing it edgewise, but sometimes the planet is tilted toward us enough, that's what's happening now, that you can see the rings go clear around the planet. Well, not quite. You notice that right at the back of the planet, Saturn's body does interrupt the rings. But next year, we're going to be able to follow the rings continuously around. So that's really how you gauge the degree of tilt in any particular year during that 29.4577 year orbit of Saturn, where it has this cycle over and over again.
These are just incredible images. I mean, it looks Saturn through the telescope. It has those beautiful sort of pastel colors. You can get a hint of that here, but it doesn't seem to have the sort of storms really that we see on Jupiter, like the Great Red Spot, does it?
No, quite right. And that's because its upper atmosphere, it's just not the stuff is not happening in Saturn's upper atmosphere the way it does on Jupiter. Now, those are two very different worlds. On Jupiter, we see all that marvelous detail through the Slooh telescopes, ever-changing festoons, swirls, curlicues, white spots, dark spots, red spot junior. The white spots tend to be longer lived, and the dark spots shorter lived. There's lightning in the white spot. I mean, all sorts of things, rising air, falling air. No, on Saturn, what we've got is a much more bland, even surface, except for that white belt around the equator, and one strange white storm that seems to develop once each revolution around the sun that comes around for a period of time. So look for that and see if that reoccurs. But I'm still looking at those rings, how we can see ring within ring, including that innermost C ring. Obviously, somebody without any imagination on the IAU, that's the International Astronomical Union, that's the official body that names things, to name these glorious rings, and this is much larger than Earth. Saturn's 95 times heavier than Earth and much larger in size. A, B, and C, surely they could do better than that. But that's how we do it with the universe. The names rarely live up to the glory. Jupiter's giant hurricane, Earth 3 times the size of Earth's storm, although it's shrunk to 2 times the size of Earth recently. We call it the red spot.
It's
It's what
functional.
we
It's
do.
functional, Bob. It works.
It's fine. Yeah, it works. It works.
These amazing pictures of the storm actually at the North Pole, and that is Saturn. As we were talking to Professor Lunine earlier, it's just full of these unusual, weird, bizarre sort of features, isn't it?
Yes, I would have loved to hear his opinion of what that hexagon is, and I know we showed that to you earlier. And this is a composite taken by a time lapse of the rotation of Saturn. Saturn has a very similar spin to Jupiter's. Its equator goes around in 10 hours 14 minutes, and the poles in 10 hours 40 minutes. Not too dissimilar from Jupiter's 9 hours 50 minutes, but it's differential. And so that means that you get a faster spin around parts of the planet, the equator, than you do around the poles. And with all that wind, tornado level winds blowing right through that storm that is producing this strange hexagon, how do you get a 60-mile high, because that's what it's estimated, like a cliff, 60-mile high, sticking up from the rest, hexagon that manages to resist all those winds that are blowing right through it? And it's been calculated that the hexagon actually rotates at the same speed as the innermost, perhaps even solid innermost core of Saturn. So weird stuff going on. When we see it, it's not just beauty, it still has quite a bit of mystery.
As we're looking at these live images, the view's kind of undulating, and one moment it's slightly blurry, and then it sort of sharpens up. What's going on there, Bob?
I love it when you ask that, because you're as skilled an astronomer as any on the show, but just like the David Letterman who just retired, he would ask questions and he'd darn well know the answer, but he'd ask them to draw it out. And what's happening is our own atmosphere. People who've been watching Saturn ever since Galileo first did so through a telescope in the year 1610 have found that our own atmosphere, of course, the same thing that makes the stars twinkle makes the planets blurry 1 second, clearer the next, maybe blurry for a whole minute or two. Sometimes we get bad luck and it's blurry for an hour or so. And if the telescope is located in one of the parts of Earth with very good seeing conditions, and that's what's happening on the Canary Islands with the Slooh main telescope, then you can get steady seeing for a longer period of time. And this is, you might think that, oh no, look at it's wiggling around. But no, this is actually quite good to have this kind of clarity. People with backyard telescopes can tell you that sometimes our own air gets so bad that no matter what kind of telescope you have, you can't even tell that Saturn has rings. That's how blurry it can get. So we're doing quite well.
I know lots of you are watching our show online, and you're following us via Twitter. And if you've got questions for Bob, you can ask him a question. Use the hashtag #SuperSaturn, and we'll see your tweet, and hopefully we'll be able to ask a question live on air. But Bob, I was speaking to Professor Lunin earlier about Titan and Enceladus, and really those are just two of Saturn's moons. How many does it have in total?
What are we up to? 60 something? When I was a kid, I hate to admit it, there were 9, and then we discovered the 10th, Janus, and that was a big deal. Mimas, Hyperion, they're all interesting. Iapetus looks like a yin yang. It's got one hemisphere that's much darker than the other. And so close-up pictures show that it looks like that oriental symbol of a yin yang. But the professor nailed it. The two moons that interest us are, gee, you got one that has oceans, but they're methane. Here on Earth, methane has a bad reputation. It's essentially natural gas. If you cook with gas and you turn on your stove, that's what's coming out, CH4, methane. So you got to be pretty cold to have liquid methane. And then there's Enceladus with salt, water, oceans. Are you kidding? Whole oceans that are spraying material into space that you got to wonder what's there. Here it is. Because on Earth, life started in the oceans, and there's been oceans there just as long as there have been oceans here. So, why not? Why couldn't there be life there?
I look at these images and I just think they're absolutely extraordinary. You see these fountains erupting, and you think, yeah, like you say, there must be something under the surface. Even if it's not life, and maybe it's just the sort of ingredients for life as we know it. It must be a really interesting place to be deep under that surface and see what's underneath there.
Yes, and I'm glad you used the word ingredients, because what we humans like to do with sea life is generally to eat them. So we can only hope that Enceladus has shrimp and lobster, because it's time to go there and start harvesting these things. And you can imagine a seafood restaurant specializing in Saturnian crustaceans and other delicacies.
I can imagine you'll be the first person to set up a seafood restaurant on Enceladus. That's how it would go down in history.
Yes. Oh, and here's our live view again. You can't get tired of this. This is just
no, you can't.
The most distant of the ancient planets. Now, its reputation was bad for a long time. There's no getting around it, because since it was the farthest planet known and the slowest moving planet, I mean, the one just in front of it, Jupiter, takes only 5.2 years to go completely around the sun, and therefore completely around our sky. But Saturn takes almost 30 years. So the ancients said, well, its influence on us must be heavy and sad to be moving so slowly. It must be depressed. And we even have the word Saturnine to describe somebody who is lethargic and a little depressed. Jupiter, though, was much more lively and it was brighter, so we even have the word jovial to describe it. So each of these planets had a mythology connected with them. And Saturn's mythology was one of sluggishness. But when we actually see it now through the Slooh telescopes, we can see how wrong that thought was, to think of it as something depressing or sad, because it's just nothing short of glorious. It doesn't take any editorializing to enjoy this. Just look at that. And during the moments that it steadies up, I'm so glad we're showing these images live as they're happening in real time. And each second, there's a different degree of clarity, because each part of Saturn's image is coming through our own atmosphere. And as it passes through colder air, each bit of light has to bend or refract in one direction. When it passes through a little bit of warmer air, it refracts in a different direction, because cold air has a higher index of refraction. So because of that, traveling through our different air layers, look at the result. We're seeing this seeming turbulence, but in between, notice that there are moments of exquisite sharpness and moments when it's a little blurrier. And that's not our equipment, that's not our internet, that's not anything but the actual live view of Saturn as its image traveling for 10 times, well, 9.5 astronomical units means it's 8.5 Earth-Sun distances away from us. So long time, over an hour for the light to get here.
In those brief moments, you can just see the Cassini division, which is that dark line between the main rings there. It just snaps
Yes.
into vision very clearly.
Quite so. And the rings are extraordinary. They're analogous. They're so thin relative to their width that they're analogous to a sheet of paper the size of a city block. Just imagine the thickness of a piece of paper compared to a size of a city block. And those are the rings. And here we see them edgewise, a view from the Cassini mission, just showing you how thin they are. So thin that an astronaut who is spacewalking could pass from the northern side to the southern side in about 5 minutes. It would require,
You're almost invisible.
compared to the length, which is something like 100,000 miles. So quite something.
Now, this is kind of like a view looking backwards. This is taken from the Cassini mission, but I don't know if you can see on your screen, Bob. I can, because the image is quite sharp on my screen, but there's a tiny, tiny, barely a pixel-sized dot just to the bottom right of Saturn's disk there. And that is the planet Earth. This is a picture from Cassini looking back towards the sun, back towards the inner solar system, and seeing sort of Saturn silhouetted. But that's us. That little tiny pixel, that's us there looking back at Saturn. It's quite incredible, isn't it, that we've actually got a probe out there that can take such a picture.
Yes, and the sun backlighting everything. And so in other words, what we're seeing is a total eclipse of the sun by Saturn. And so the rings, and it's really revealing to us the different opaquenesses, opacity would be the real word, of the ring material. And so you can see that the B ring has some much thicker material that totally blocks the light. And you can see that the different parts of the rings, they're all little chunks of ice, we said that, but they're all in orbit around Saturn's equator. So each one is a little moonlet that's orbiting Saturn itself.
And what I love about this picture is that we've got in our live views, you can see the sort of main rings themselves, but this really draws out those fainter outer diffuse rings. I mean, we talked about those jets from Enceladus releasing all that water. Well, that water, that water ice, I should be more careful, those particles basically create that ring, don't they? That's what we're seeing in that beautiful diffuse sort of glowing ring.
Yes, it's just stunning. So we have a very dynamic system going on. You know, these aren't objects that just sit there inertly and don't do anything. This is a very active system. The moons are all interesting. The object itself is, and there we go to our live view again of Saturn. On this night, when it's both at its closest to Earth, and that means it's brightest and biggest, and proof of that, we can prove it. Look at the ball of Saturn, and then look behind it to see its shadow being cast on the rings behind it. Can you see its shadow? No, not really. And that's because we are right in between Saturn and the sun. That's why we say it's in opposition tonight, because the sun is directly to our back as we're now looking at Saturn. we're in a straight line, and that means that shadow, of course, since the sun is right behind us, must be cast straight back. Here's a nice view taken from above the North Pole of Saturn by Cassini, showing the same effect of the shadow being cast off to the left onto the rings. And you noticed before the show we were talking about how there's a faint glow on the night side of Saturn. That's actually the ring material, which is brilliant. The rings contribute more than double the light of Saturn itself, um, and are lighting up the nighttime hemisphere. But I can't look at anything but that hexagon. You know, you look at that strange hexagon, far larger than the planet Earth, and we know it was there because when the Voyager spacecraft, both of them, Voyager 1 and 2, which passed by in 1980 and 1981, looking at the archival images, that hexagon was there even way back then. I was glad to see Professor Lunine, by the way, say that that's what gave him his start, was Voyager 1 going past Titan. And that has erased something that has bothered me now for decades, because at that time, 1980, we had two spacecraft a year apart visiting Saturn. Voyager 2 had a failing radio and was using a backup radio. And we had hopes that maybe it could get to Uranus, which it did in 1986, and maybe even Neptune, which it did in 1989. But who knows if it was really going to survive and make it. Voyager 1, which was in perfect shape, was sent sideways to take a close look at Titan, and we saw nothing. Its moon was covered with a thick opaque atmosphere. We could see no detail. And I was not alone at the time in 1980 saying, I was in college at the time saying, what a waste. We sent this one spacecraft sideways, which meant it could not go on to any other planets. The mission to the outer solar system was over for Voyager 1 just because we wanted a close-up of Titan, and we didn't see a thing because it's just a blurry mess because the atmosphere is so thick. So only now tonight, since 1980 till now, what is that, 35 years, that's bothered me. And only tonight have I been able to drop that because he said that that event is what started him on his lifetime of focusing on Saturn professionally. So, hey, some good came from that.
Yeah, you feel vindicated.
Yeah.
Great. The interesting thing about the rings actually is they change their angle, don't they? I mean, this view that we're seeing is very particular to this time in Saturn's orbit.
Oh, yes, absolutely. During that 29.5 year orbit, the axis keeps the same tilt. It's a few degrees more than our tilt. And that means that since it's always angling the same way as Saturn goes around the sun, sometimes we're seeing it edgewise. Sometimes we're seeing the opposite hemisphere, the southern hemisphere, and sometimes the northern. The southern is the better hemisphere. I mean, Saturn files know that because whenever the rings are tilted the other way, which is every 15 years we get the opposite view, it just so happens that that occurs when Saturn is highest up for people in the northern hemisphere, like myself, and especially you, in other words, Europeans and Americans. Saturn will be in the constellations of Taurus and Gemini and Cancer, much higher up and better observed. And Saturn is at the perihelion part of its orbit, the closest part to its orbit, so it becomes larger and brighter, it's higher, and all those things come together when we see the southern side of the rings. Right now we're seeing the northern side, and so it's kind of a raw deal a little bit because the opposite happens. It's low in the sky in Scorpius, it's farthest away. Nonetheless, it's not too shabby, is it?
No, absolutely not. I mean, it's one of those things that you have to, here in the UK and certainly in Europe, you have to stay up a little bit late to see. But if people missed earlier on when we were talking about where to actually look for Saturn, I don't know if we've got the live all-sky view from the Canary Islands that we could bring in.
There it
How do we
is.
go about finding Saturn this evening, Bob?
Yes, look at the bottom of the picture, and the brightest star at the bottom is it. So wherever you are during the first few hours after nightfall, just look to the southeast, and that bright star is it. One of the ways you can tell for sure is that right to the left of that star are three stars in a row of about the same brightness. Those are the stingers of the scorpion, made Beta and Delta and Pi Sky. Another you can tell for sure is that bright star to its left, one of the brighter stars of the sky is Antares, the famous rival of Mars. That's what its name means. Ares was the Greek name for Mars. Ant means, like an antonym. It means that's something that's opposite. It's a rival of Mars because its color so closely matches that of the planet Mars. So there it is. It's right to the upper right of Antares these nights. Look how bright that is. It rivals Vega near the top of our picture, the brightest star just to the left of center at the top of the picture. The brightest of the summer stars is Vega at magnitude 0, and Saturn is just about at magnitude 0. So it's really standing there as among the brightest stars of the sky because this is it. The the night when it's best. But that doesn't mean you should give up because it's going to stay good for a couple of months. It's just this is the very best night, but it'll only be slightly less bright and slightly less large through our Slooh telescopes in the weeks and even the next 2 months to come. Here's
Okay,
our
well, as
live
we
view
look at
again.
these live pictures, we do have a question from Twitter from someone who's been watching along to the show, and they use the hashtag Super Saturn. And Bob, it's a interesting question, and I wonder whether you want to sort of give your opinion on it. Is there any possibility of Titan sustaining life someday? What do you reckon?
Well, I don't know about someday because it's always going to be cold. The sun is 100 times weaker from there than it is from here. Sunlight falls off inversely with the square of distance. Saturn is 9.5 times our distance from the sun. Multiply 9.5 times 9.5, you get very nearly 100. And as the professor said when we had him on earlier, he seemed more optimistic. He said they're a carbon compound. He said organic. And everybody thinks
Mm.
of life when they hear the word organic, but organic really just means there's got to be some carbon there in the form of methane, for example, CH4. But could you have life when it's that cold, when it's a couple of 100 degrees below zero? Maybe. It would be a different kind of life from Earth. I'd sure like to check out Enceladus before I would check out Titan, because Enceladus has
Mm.
got warm, salty oceans, and you sure want to go to warm salt water before you want to go to 200 degree below zero methane, if you're going to look for life.
So, since we're talking about the moons, how easy is it to see them with, say, an amateur telescope?
Oh, not hardly Titan. Titan is the 8th magnitude, which means it's even visible with binoculars. So if you have steadily braced binoculars, you should have no trouble seeing a little star near Saturn, which is Titan. The others start to fall off when you get to Hyperion, Enceladus, Phoebe, Mimas. Uh, they're not in the same league. It's very different from Jupiter's moons, where you have 4 that are giant, and then all the rest are little tiny things that are 30 and 50 and 80 miles in diameter. With Saturn, you get one very large moon, 3,000 miles in diameter, and all the rest are just medium to small size. So really, one stands out from all the others.
It's really beautiful views. I'm so pleased that we've managed to get these live views from the Canary Islands, because we didn't know if we'd get them just before we came on the show. We had a technical hitch that meant that we weren't sure whether we were going to get them. But there they are. That's the live view of Saturn through the telescope. And there's an interesting effect that happens around this time of opposition, isn't there, Bob, where the rings appear to brighten. Do you think that we can see that in these live images?
Well, yes, because it's like a movie screen that, when something is exactly opposite the sun, like a highway reflector that your car headlight is hitting, we get that effect around the full moon too. The full moon reaches half its full moon brightness only 2.4 days before the full moon. So we all know that a half moon is not half as bright as the full moon. It's only 1/10 as bright. You can see that their effect on the countryside. And then the moon explosively brightens starting 2.5 days before full moon because same effect. Sunlight's going straight down on its surface and shining straight back, erasing all shadows and acting like a movie screen. Same thing here. The Saturn brightens up in particular around the time of its being opposite the sun, and that's what we've got tonight. So it's quite lovely, quite bright. Amateur telescope using Slooh. naked eye, almost anything you want. I'd say the only thing that's a little disappointing is binoculars, because they won't do anything for you, because you really require at least 30 magnification, 30 power to see the rings, and binoculars don't reach that.
Okay, well, we're nearing the end of our sort of live show looking at Saturn. Bob, do you have any sort of final thoughts about the things that we've been seeing this evening? Maybe the discussions we've had about life on some of these moons.
It's just so exciting, Will. I'm almost speechless. I should be speechless, because when you're, when you're faced with great beauty like this, if you visit the Grand Canyon, or if you see a total eclipse of the sun, you don't want to be yakking, because it's almost a sacred experience. It's so beautiful, and so when you ask me my thoughts, it's more like my non-thoughts. It's just how gorgeous this thing is.
That's a lovely sentiment to end with. And thank you to everyone who's tuned in to watch the show. And I know you've had lots of great questions on Twitter. Thank you for basically watching the show. And our next public show is coming up on June the 11th, where we're going to be looking at Uranus photobombing the moon. And if you're a Slooh member, you can get another show tomorrow, in fact, as we'll be looking at Neptune returning to the evening skies. We'll be watching it rise. So if you're a Slooh member, you can watch that as a Clubhouse clip live in the Clubhouse. But from us here on Slooh.com, thanks very much for watching, and we'll see you again next time. Good night.
A huge part of Slooh's mission is popularizing astronomy. That's why we decided to have an outreach beyond the robotic telescopes our members use. We became webcasters. Our shows reach millions of viewers worldwide, with some special shows reaching tens of millions. Here are a few of our favorite moments.
Hello to everybody watching and joining us this evening. When I see this image, I'm just blown away. I mean, this is fantastic. I'm watching a comet live streaking through space.
We're looking here at live pictures from the Canary Islands showing that beautiful glowing green coma of the comet, and also even a hint of the tail. Despite the moonlight, we're seeing the beautiful streamers in the tail of the comet there.
I'm holding up my cell phone. It's showing a movie of the images we got at Goldstone last night.
Wow, that's incredible. So that's what it looks like.
This is what it looks like.
The last time Venus crossed in front of the Sun, the year was 1882. World War I lay 30 years in the future. Since then, no one had observed the nearest planet to us partially eclipsing the Sun until June 8th, 2004. These images represent hours of live views compressed into a matter of seconds.
There he is.
Oh, there it is.
There it is.
Yeah.
There it goes.
Yeah.
So
Have to use much higher exposure than before.
This is quite nice. Now, the moon is moving about 2,287 miles per hour. Now, we're talking about several times the speed of sound, not crazy fast. And that's what's producing this, the actual orbital motion of the moon as it now slides and reveals the distant planet Saturn.
One of Slooh's most popular events was the total lunar eclipse of December 21st, 2010. This rare totality on the day of the winter solstice, when the moon ascended to its highest point in the sky, fascinated the mass media and the public alike. Slooh assembled a team of astronomers and commentators, while its own observatory instruments, as well as remote telescopes, remained trained on our nearest neighbor in space as the moon plunged into Earth's shadow.
This is it. This is the minute of the solstice. This is it. 3 minutes after 6. Happy solstice, everybody. Happy solstice. There it is.
And as you can see across the pictures here,
that is the exact spot where the flare erupted from the active region. You can see it brightening, and that is indeed what a solar flare is.
I love the fact that you have the special camera to see the hydrogen alpha view of the sun, so to see the chromosphere. I think that's a really lovely way to view a partial solar eclipse. Total solar eclipse are much more intriguing and exciting for me, because then we can see the corona, the atmosphere of the sun revealed, and there's lots of science that we want to do by studying the corona, but still partial solar eclipses are tremendous.
NASA and the world is becoming more and more aware that it might be a good idea to track near-Earth objects, hazardous potential impactors. And what is your next project? What do you intend to do with studying these planetary impacts and the potential for global catastrophes? What's next on your to-do list, Dr. Boslow?
Well, I'll tell you what I would love to do, and that's to collaborate with you guys. Because what I'm really interested in are these objects, not that are discovered way in advance, but the ones that are discovered on final approach.
Actually, amateurs have played a strong role in tracking asteroids for many years.
Did your time in space, peering down at our home planet, change the way you thought about Earth's vulnerability, Ed?
Absolutely it did. It actually works both ways. It makes you understand and appreciate that the Earth is really part of something much larger, and you appreciate when you look at the moon at the same time as you look at the Earth, which you can get that view from space, that the Earth is hit by asteroids all the time.
Even after these 40 years. We're not going back. I'm not saying that that's bad. By the way, hey Matt, did we just see a plane?
Oh, I just saw a jet. Whoa!
Yeah,
dude,
yeah, you did. Well, anybody who doubts that we don't have live images here, there was the proof of it.